The next idea in 4.2 that I wanted to discuss is scientific notation, another thing that I'm assuming you guys are familiar with, but I just wanted to talk about real quickly because it's very, very important, not just to math, but also to the sciences. Because often in those classes, we're dealing with numbers which are very, very, very large or very, very, very small. And before I get into defining scientific notation, I wanted to just talk about, well, what's the idea behind scientific notation? Why does it exist, and why should we care about it? But if you think about numbers of different sizes, a lot of times in math class, we deal with numbers like 1, 3, 10, 25, numbers which aren't too large or too crazy. But in the context of the real world, a lot of times things are really, really, really far apart, or things are really, really, really small, and we often need numbers that are very, very big or very, very small to try to describe something that's going on. And obviously one of the weaknesses to really, really big or really, really small numbers is that if I'm trying to write out an equation or do math, it's really, really impractical because of how long it takes to write the number out. And so numerosity is just a term for like how big is a number, and scientific notation is a way of trying to extract the numerosity from a number itself. And scientific notation is how we do that. So like, say for example, I was looking at this number right here. The commas are a very common way that we describe, that we separate the scale of those numbers based on the different periods, which is just a term for the different groups. It's supposed to be a way to help see, well, how big is this number? But like, if you're like, a lot of people, when they look at numbers that are really, really big, their brain just runs into a dead end. It's like, okay, this is too big to even consider. But if I'm looking at it, the commas are trying to help. Well, this is 1,000, million, billion, trillion, quadrillion, quintillion. Basically what this is 42 quintillion. It's very, very big, and a lot of people don't even know that those know the names for numbers that are that large. But ultimately, how is that any different than 42 billion or 42 trillion or quadrillion? It's just really, really big. And obviously more and more zeros means bigger and bigger and bigger. And actually, just as a fun fact for you guys for right now, in other countries, for example, Germany is one, I believe, they actually use the decimal point to separate the period of numbers like this. And they actually use a comma to differentiate between the whole place and the decimal places, the fractional parts of the number. And it can be a little bit weird, but if you look at math from people that are from those countries, it will be 42.000.000.000, and it'll be really weird because you expect it to have this. And then when you say you wanted to describe $42 to them, it would be 42,00, because the comma and the decimal place are just used for exactly the same thing, but opposite. Now, obviously, like if a number was really, really, really small, like 0.0000042, again, well, how would we call this number? Well, and also, if you've ever wondered why don't we use commas for really, really small numbers, there's no reason you can't, but notice that it's not exactly a synonymous thing, because when I go to the first place beyond the decimal point, technically the thousandths place is not 3 over, right? Like right here, 3 over is the thousands place, but when I go the other way, this would be tenths, hundredths, thousandths. So it might make sense to put a comma right here, but it'd be kind of weird because it would be after 2, and then I would have thousands, 10,000ths, 100,000ths. Then this would be millionths place. Then right here would be, let me make sure I do this. So tenths, hundredths, thousands, 10,000s, 100,000s, millionths, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillionths, 10 trillions, 100 trillions, quadrillionths, 10 quadrillions, 100 quadrillions, quintillionths. And again, the only difference is the TH. Then I have 10 quintillionths. Then this would be 400. And I already lost track, but it's not important. You get the idea. It gets smaller and smaller and smaller, and it's always by a factor of 10, just as when we do really, really big numbers, it's by power of 10. But anyways, the whole point of scientific notation, sorry, I got really off topic talking about how the names of these numbers. The point is it's really, really big and really, really small. and it's impractical to write it out. Scientific notation is a very convenient way of extracting the numerosity from the number and just writing it using the relevant power of 10. Because one of the great values of our place value system is that all of these numbers, well, this is 42, what did I say, quintillionths. That's equal to 42 times 1 quintillionth. Or if I was to take 42, that would be 10 times 10 times 10 times 10 times 10 times 10 times 10. And basically I could write them using powers of 10. And so this first number, if I was to put it in scientific notation, I'm sure you guys know how to do this, but basically you put the decimal place here and you want to know how many places has the decimal moved from here to here, which would be a total of 19 spaces, which is why it's times 10 to the 19th. And again, why it's positive is because this would be 4.2 times that, and it gets bigger and bigger and bigger by that many tens. And now if I took 4.2 and divided by that many tens, the decimal would move the other way, right? Because if I divide by 10, I get tenths, and then hundredths and thousandths, and so on and so forth. And if I kind of check, well, the difference between the decimal place being here and here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, if you count it up, that should be 20. Again, assuming I didn't miscount when I made these slides previously. It would be an equivalent value because, again, this would mean 4.2 divided by 10 to the 20th, divided by a bunch of tens, and dividing by tens always moves the decimal place to the left, whereas multiplying moves the decimal place to the right, creating big numbers or really, really small numbers. And at the end of the day, the last little bit about the value of scientific notation is if, say, I wanted to multiply these numbers or divide them, these are now powers of 10, and I now know how to multiply or divide them together because they are exponentials. So let's say I was going to multiply this number times this number. This might, cause you into math breakdown where you're like, I don't want to even think about multiplying these numbers because they're so stupidly big and small. But basically, if I just wanted to multiply this times this, well, what I could do is I could multiply what those numbers are, 4.2 times 4.2, which would be a little bit easier, and I could multiply this. And if I multiply these, I would just add the exponents. That would just leave me with 10 to the minus 1, and this becomes a lot less scary of a thing to figure out. And in science, numbers like this are so common, really, really big and really, really small numbers, that it's so much more helpful to use them. And also when I'm looking at this, like a lot of students are able to use scientific notation, but it's in my experience, it can be kind of hard to really extract, well, what's the meaning? But just knowing your powers of 10, like 10 to the third is 1,000, 10 to the 6th is 1,000,000, 10 to the 9th is trillion, 10 to the 12th, quadrillion, and wait, sorry, I skipped one, 10 to the 12th, trillion, 10 to the 15th, quadrillion, 10 to the 18th, quintillion. But basically I can kind of imagine how big these numbers based on the power of 10, and I could really understand this is really, really freaking big. I mean, and 10 to the minus 20th in the same way is really, really small. And each power on there is another decimal place difference.